Hey everyone, so this week we're going to be looking at significant figures and precision and accuracy. Not the most related topics, but both can be pretty important in general chemistry, and they definitely lean on the more conceptual side as opposed to the more math-heavy stuff. So definitely important topics to cover for general chemistry. So, significant figures. What are the rules? For starters, the easy one is that all non-zero digits are significant. The hard part is figuring out which zeros are significant and which ones are not. So zeros are significant if they are either sandwiched between two non-zero digits or sandwiched between a non-zero digit and a decimal, or if they follow a non-zero after a decimal place. Now that we know some of the basic rules for figuring out if a digit is significant or not, let's try some examples to see if we can determine the number of significant figures in a bunch of different numbers. So we'll start with 402. We have these two numbers here, which are obviously non-zeros and therefore significant. And then we have this 0 in the middle, which is sandwiched between the 4 and the 2. This means that we have three significant figures. The same is true for a number like 10,132. We have these four non-zero digits and a 0 sandwiched between them, so we have five significant figures. The other part of that rule is that a 0 is significant if you are sandwiched between a non-zero and a decimal. So for example, if you had a number like 40.2, even though the 0 is sandwiched between the 4 and the decimal place, we still have three significant figures here, because the 0 still follows the sandwich rule. So now that we've looked at the first rule a little more in depth, let's move on to the second rule, which says that zeros following a non-zero after a decimal point are also significant. So if I wrote something like 0.400, this has three significant figures because you have the 4, which is a non-zero and automatically significant, and then you have two zeros that follow it after a decimal. So that means that these zeros are significant. Another way to think about this is in terms of zeros that are not significant. So the rule of thumb for zeros not being significant is if the zeros are only there to determine the order of magnitude that your number is going to be. So for example, if you have a number like 0.0043, none of these zeros are significant because all that they're doing is pushing your 4-3 around to determine the order of magnitude. The same is true for any number that is 0.0, however many zeros, and then your actual numbers. Let's say it's 6 in this case. No matter how many zeros you put in this blank, this number will only ever have one significant figure. Now, the trailing rule still counts here. So if you had, let's say 0.0, some very large number of zeros here, and then 60, this has two significant figures because we're following the rule shown down here. So both of these digits are significant. Now, the best hack for figuring out the number of significant figures is to just write everything in scientific notation. And the reason I say to write everything in scientific notation is because the zeros that only determine your order of magnitude go away when you write numbers in terms of scientific notation. So let's go back to this number. I'll write it down here again. If you're looking at this and wondering to yourself, okay, what's another easy way to remember that this is only two significant figures? If you write this in scientific notation, which is 4.3 times 10 to the negative third, it becomes a lot more obvious that this has two significant figures. The same is true for larger numbers. So if we have, say, 400, this also only has one significant figure because there's nothing sandwiching these zeros. But again, another way to think about this is to write this as 4 times 10 to the third.
Nope.
And again, it becomes clear this only has one significant figure. So if a zero's only purpose is to place your non-zero digits, then the 0 is not significant. However, if the 0 is sandwiched or follows a number after a decimal place, then it is in fact significant. Now that we know how to determine the number of significant figures in a given number, we need to look at determining how do we use those significant figures to do rounding when dealing with calculations. So There are two different sets of rules here, one for multiplication and division, and a separate rule for addition and subtraction. So we'll start with the multiplication and division rules. When you're multiplying or dividing with significant figures, the number of significant figures you use in your final answer will be equal to the number of significant figures of the number that you are multiplying or dividing that is smallest. So for example, if we're going to multiply 0.25 times 124, the true number that you get when you plug this into a calculator is 31. 0.25 has two significant figures and 124 has three significant figures, which means our final answer needs to be in two significant figures. Well, in this case, this is already two significant figures, so we don't need to do anything. We can leave the answer as is. Now, where things can get a little more complicated is, let's say we're multiplying 125 times 16. We have a number with two significant figures and a number with three significant figures, so we already know our final answer will have to have two significant figures. However, when you plug this into your calculator, it comes out to exactly 2,000. That only has one significant figure, and we can't just slap a decimal point here because now we're suddenly at four significant figures. So this is where writing things in scientific notation can come in handy. When you're writing numbers in scientific notation, you have complete control over the number of significant figures in your answer. So if we just write this as 2.0 times 10 to the fourth, suddenly we have the correct answer in the correct number of significant figures. So the rule of thumb is, when in doubt, always, always, always write your answers in scientific notation. So moving on to addition and subtraction, the rule here is a little bit more complicated. You need to look at the order of magnitude and the smallest order of magnitude that is certain for both numbers involved in your calculation. And this is probably easier shown in terms of an example than being explained. So let's say we want to add 0.01, we want to add that to 0.008. Between these two numbers, the order of magnitude that is certain for both of them, for this number, it's the thousandths place, but for here, it's only the hundredths place, which means that even though adding these together normally gives us 0.018, we need to round this to the hundredths place because that is the order of magnitude that is certain for both of them. So this then rounds to 0.02. So unlike multiplication and division, addition and subtraction doesn't necessarily have to do with the exact number of significant figures, but it has to do with the level of precision between the two numbers that you're looking at. So another example of this would be, let's say we're going to take 400 and we're going to subtract 21. Your true answer here is 379. But again, we need to look at the order of magnitude that is certain. And in this case, the largest order of magnitude that is certain is the hundreds place because these zeros are not significant. So even though the final answer here comes out to be 379, when you round according to sig fig rules, your answer is actually 400. So another example, if we want to add 120.57 to 17, again, the true answer that we get out of that is 137.57. The smallest order of magnitude that is significant within this calculation is the ones place of the 17, because there is no decimal place, there are no significant figures beyond the ones place. So this answer must be rounded to 138. So when you're dealing with addition and subtraction, the only reason that you need to worry about the exact number of significant figures is because you need to know the order of magnitude corresponding to the appropriate significant figure. That's what makes this particular example really tricky. It's because you need to know that these zeros are not significant figures. As a recap of significant figures, remember that zeros used to determine the order of magnitude are not significant, and sandwich zeros or zeros following a sig fig after a decimal place are significant. And when in doubt, always, always, always use scientific notation. Now that we've covered significant figures, let's move on to precision and accuracy. When a lot of people talk about precision and accuracy, they always bring up the target example. The thing to remember is that accuracy only cares how close you are on average to your true target value. How close are you to the center of the target? Precision, on the other hand, looks at how consistent you are across your measurements. How close is your grouping? So for example, you may have a grouping of measurements that all end up out here, where you are not accurate, but your grouping is relatively tight, so you're still precise. For accuracy, you might have some measurements that are really close, such that your average is really close to the true center, but you're not quite as precise because your grouping is not very tight. Something to keep in mind is that you can be precise without being accurate, as we see with this grouping up here, and it is possible to be accurate and not be precise. These two things do not depend on each other. Keeping this in mind, we're going to look at an example of an experiment that some students will do in general chemistry, where you look at the accuracy and precision of different measuring devices inside the lab. In this experiment, we will take 3 different measuring devices: a 10 milliliter graduated cylinder, a 50 milliliter Erlenmeyer flask, and an 80 milliliter beaker. We're going to measure 10 milliliters of water in every single container, and then we're going to weigh that water to see what the true volume of that water is. And then we can look at the accuracy and precision of each of these 3 containers. Since the density of water is just 1 gram per milliliter, conveniently the true volume is going to be exactly the same as the weight that we measure. So then we want to take the average and standard deviation of these 5 data points for each of the containers to see which of the containers is the most accurate and which of the containers is the most precise. So in this case, your average is another way of looking at accuracy, because accuracy is concerned with how close you are on average to the target value. In this case, the target value is this 10 milliliters that we were measuring. So if you look at the 3 values here for the 3 containers, you'll notice right away that the closest value we have to 10 is 10.004, and that is for the 10 milliliter graduated cylinder. So we know that this graduated cylinder is the most accurate of our 3 containers. Your standard deviation is analogous to your precision, because it looks at how tightly grouped your measurements are. Now you'll notice here, between these 3 values, that it's actually the 50 milliliter Erlenmeyer flask that has the best precision, because it has the lowest standard deviation. So, as we talked about earlier, it is completely possible to be accurate without being the most precise. And it's also possible to be the most precise without being the most accurate. Unfortunately for Mr. 80 milliliter beaker down here, he is definitely the least precise of the 3, but he's actually not the least accurate. The least accurate is in fact our Erlenmeyer flask, which happens to have the highest precision. Hopefully this experiment, along with the target analogy that everyone else uses, you have a pretty good understanding of both accuracy and precision and how they are different from each other and how to compare them from experimental data. Well, hopefully that was helpful, and we will see you next time on the Drawing Board by TBPi.